Now we will introduce a theorem, another way to help us identify whether a subset is a subspace or not. So let's call the theorem. The theorem one says this, all right? If V1 to VP are elements in vector space V, then the span, the set formed by all possible linear combinations from V1 to VP, is a subspace of V. All right, we call the span V1 to VP the subspace spanned by or generated by V1 to VP. Okay, so given any subspace H of V, a spanning set for H is a set from V1 to VP. It's called a spanning set. All right, so this H can be the spanning set from V1 to VP. So if we can show that any set is a span from an element from V, then this set itself is a subspace. We can prove that in general. Okay, all right. That's just in general, right? So we have done that before from the previous example. So let's look at a recap. All right. To show that H is a subspace of a vector space, use theorem one, meaning if a subspace, a subset, I don't know whether it's a subspace or not. If I can show that V1, find some element from V1 to VP, which is V1 to VP, is an element of the vector space, and I can show that H is all possible linear combination of these elements, then H itself automatically qualifies as a subspace. Second, to show that a set is not a subspace of a vector space, all you have to do is show that at least one of the axiom, which is A, B, and C, 0 is not there, not close under addition, not close under scalar multiplication from the definition of subspace. You can show one of the element is violated, then that set is not a subspace of a vector space. Let's look at an example. All right, we have a set here. V consists of two elements. Okay, A plus 2B and 2A minus B. A and B are any real numbers. So is such a set V a subspace or not? Well, we can look at this. So you can look at A plus 2B, 2A minus 3B. All right, we can separate them according to A and B. So A or B are any real number. And after that, you can factor out A from the first one, factor out B from the second one. Well, V1 and V2 obviously belong to R2, right? They are two vector spaces and they are not parallel to each other. Okay, so 1, 2, 1, 2, and 2, 2, negative 3, 1, 2, 3. So they are not parallel to each other. So if A and B are any real number, obviously this vector is all possible linear combination of 1, 2, and 2, negative 3. Therefore, from the previous theorem, it automatically is what? Is a subspace. Okay? And another one, look at another example. All right, now we have in R3, A plus 2B, A plus 1, and A. Is this a subset, a subspace or not? Well, let's check the first one. If you have to be 0, that means all three have to be 0, right? Well, look at here. If A equal to 0, obviously A plus 1 does not equal to what? 0. Therefore, 0, 0, 0 is not in the subset of H. That disqualifies H as a subspace. What about this? Let's look at the 2 by 2 matrix. 2A, B, 3A plus B, and 3B. Again, we try to see if we can find, can identify this as this 2 by 2 matrix as a linear combination of something. So if we separate them according to A's and B's, then we can factor out A's and B. Well, obviously 2, 0, 3, 0 belong to M as a 2 by 2 matrix. 0, 1, 1, 3 belong to a matrix of 2 by 2. Therefore, this is a linear, so this set right here is a all possible linear combination, because A and B are any real number, of the two matrices belong to a 2 by 2 matrices set. Therefore, this set H, you can say H is spanned by these two elements. So H is what? Subspace. Here are the exercise.